For today's lesson, we are going to split it in two halves. The first half, we're just going to look at the equations that we've covered. So it's just going to be a quick summary of the equations we have covered. 3 equations looking at how we represent them. Then we are going to come across a 4th equation, which will lead us into how thermal energy behaves in a system and how we can describe the various ways in which thermal energy moves through a system. So first I want you to put the title, summary of equations, and can you put today's date? And also, can you put the subheading learning questions? And I would like you to answer these 2 learning questions that you see here. So the first one is, state what EK and EP stand for in energy equation. So there are 2 equations, and I want you to identify which one belongs to EK and which one belongs to EP. That is 2 marks. The next question, question 2. For an efficiency value, which one is true? So if you are calculating efficiency, which of the 3 values would be true? And I want you to explain your answer. So you've got an efficiency value of 1. Then you've got an efficiency value of 0.72 for B, and C, an efficiency value of 2.01. So which one is true? And I want you to explain your answer. So we'll take 5 minutes for this. Can you set out your work and answer the 2 questions? So let us cover the answers for question 1. EK stands for kinetic energy. So the equation for kinetic energy, and EP stands for gravitational potential energy. So I'll repeat again, EK stands for kinetic energy and EP stands for gravitational potential energy. So this equation here is for kinetic energy and this is for gravitational potential. So moving on to question 2. For an efficiency value, which one is true? It would be this one here, 0.72. This is because efficiency can never equal 1, because you can never have a system that is 100% efficient, and it cannot be C. You cannot have efficiency going above 1, as you would be creating energy. Okay, moving on now. So now we're going to look at kinetic energy. Here we can see a quick recap, a quick breakdown of the equation for kinetic energy. Kinetic energy is used to calculate the energy of a moving object, and the equation is half mv squared. And I've showed you the equation in a word format and also in its broken down symbol format. So you can have EK equals half mv squared, where m equals the mass and v equals the velocity. And the units of kinetic energy, EK is in joules, mass is kilograms, and speed is meters per second. So if your notes are missing the equation with the units, you must make sure that you have the units and you have the equation in your notes clearly written down, specifically the units as well, because you, without assigning the correct unit to the correct value, you will lose 1 mark or more, depending on what the examiner is looking for. So can you just take down the summary of kinetic energy in your notes if you do not have it clearly already in your notes? Those of you that do have it clearly in your notes, what I want you to do is I want you to put a formula triangle. I want you to construct a formula triangle based on how we looked at formula triangles previously for kinetic energy. See if you can construct a formula triangle. This is just a bit of extension. For those who are comfortable with the equation here, can you construct a formula triangle? So a formula triangle for kinetic energy can be represented as this equation here. So if you are struggling to put down the formula triangle, Here it is represented here. I'll just zoom in so you can see it. So this is the equation for a formula triangle for kinetic energy. So can you take this down in your notes as well, please? Those of you who struggle to put down the formula triangle for kinetic energy, can you take this down? Now we move on to gravitational potential energy. This is the energy that is stored as objects are raised above the ground. So above the ground, above the surface of the planet, as we raise objects to any given height, there is a certain amount of gravitational potential energy which is stored. The equation for gravitational potential energy is mgh. EP equals mgh. In a word format, it would be mass times gravitational field strength times height. Now remember, the units for gravitational potential energy is joules, as is the units for kinetic energy is joules. And when we talk about mass, again in physics, we always refer to the units of mass in kilograms. And the gravitational field strength, the units for gravitational field strength is newtons per kilogram. Now, it can also be represented as G, which is stated here. And the value of G will be given. You will not be expected to know the value of G. You will be given the value of G based on the context of the question. If you are given a question that is not on this planet but based on another planet's gravity, then you will be given that value, and you'll also be given the value here as well. So but be aware that you must know that the units, when you calculate it through via the equation, the units for gravitational field strength is Newton per kilogram. Now what I want you to do is I want you to take this down if your notes are not complete for the equation for gravitational potential energy. So those of you who turn back to your notes in your copybooks, if you do not have this broken down clearly, I want you to put the triangle equation in addition. So once you've taken down the points here represented in terms of the equation and the units, I want you to also formulate a formula triangle just as we constructed for kinetic energy. So for gravitational potential energy, summarize the equation with the units, and then I would like you to put down a formula triangle for gravitational potential energy. So you should have this formula triangle represented in your notes somewhere, where we can see that EP equals EP, and we have a line where mass times gravity times height is represented, and we represent this in a nice simple triangle as shown here. So can you make sure that you have this formula triangle represented in your notes? Now the third summary equation is the equation for efficiency. So as we have looked at Sankey diagrams and also the equation for efficiency, we represent it as the first equation shown here, that efficiency is useful output energy transfer divided by total input energy transfer. And this will give us a value between 0 and 1. And if we multiply that value by 100, we get a percentage. Now efficiency can also be noted as useful power output divided by total power input. So you must be aware that efficiency can be represented in two possible forms, in two possible equations. Efficiency equals useful power output energy transfer divided by total input energy transfer. So we're dealing in joules. Or we can represent efficiency via the power of a device. So useful power output divided by total power input. And as I said, you will get a value between 0 and 1. And multiplying that value between 0 and 1 will give you a percentage. So you should be able to express it in either way. Now we'll move on to how we can actually define power in terms of the equations. Now, I did say that we would go on to thermal energy, but just before we go on to thermal energy and look at specific heat capacities and the change in an energy of a system, I just want to look at this power component of an appliance or device and the equations associated with it, because it follows on nicely from the efficiency calculations that we were doing in class. So power, so can you put the subheading power, and can you take this down, please? Power is defined as the rate at which energy is transferred or the rate at which work is done. Okay, so I'll repeat that again. When we define power, we are looking at the rate at which energy is being transferred or the rate at which work is done. Now, we can understand energy transference because we have been looking at energy being transferred from one form to another in various systems. For example, in a TV, we were looking at how electrical energy is transferred to light and sound energy. We have looked at how chemical potential energy in fuels is transferred to give us kinetic energy for a car. So we are looking at the transference of energy. Now, when we want to think about the power of an appliance or device, we are looking at the rate at which energy is transferred. Or we can look at it in another way, looking at the rate at which work is done. So I'm going to give you a couple of equations now with their corresponding units, and I want you to take this down clearly and box off each equation for power. So here you can see the equation, the equations for power and how we can represent it. So as we've got the definition, sorry, I've covered up the definition at the top, but we're going to focus on this equation here and how we break it down. So as we look at this equation, you can see that, just make it a bit straighter, we can see that power equals energy transferred over time, and this can be represented as E over T. We can also represent power as work done divided by time taken, and work done is represented with a capital W, and again time is lowercase w. Notice which one is uppercase and which one is lowercase in physics, because if you put certain letters, when you put them in uppercase, they refer to a specific unit or a specific value that we're talking about. Power is capital P and it's in watts if you were to write it out in words, and the actual symbol is capital W. Energy transferred, so the energy transferred is E and the units are joules. Now here are the units, so I want you to remember that units are in brackets. It's a good practice to put it in so you can quickly identify when you are asked for a unit, you can separate it from your work. And work done again is W and it's in joules. And an energy transferred for 1 joule per second is equal to the power of 1 watt. So let me repeat that again. What you can see here is that an energy transfer of 1 joule, so when we transfer 1 joule per second, is equal to a power of 1 watt. So an energy transfer of 1 joule per second is equal to a power of 1 watt. So if you go back to your notes for the definition of power, which we had just before this screen here, you can see that we were looking at the rate, and this is why, because we have an energy transfer of 1 joule per second, which gives us a rate, is equal to a power of 1 watt. So putting this all together, and here you can see the definition at the top, and you can see that the equations written out in their symbol forms and their word equation to the far right. And here you can see the triangle format for each equation. So those of you who are struggling with the triangular format, here it is here. So the first one, when we talk about energy transferred and we're referring to power, we can use this equation here. Okay, so energy, and then we have a division sign, and then we have power times time, and we can put that into a triangle there. So take this down as a formula triangle when we're talking about power and we're talking about energy transferred. So if the question is referring to power and wants you to calculate power, or one of the components of this formula triangle, but the question is referring to energy transferred of an appliance or a system, you have to use this equation. If you're talking about work done, then you would use this equation. Or you would, if the question was set in such a way it was talking about work done, you would use this format or this formula triangle to actually work out your answer. Now, just to remember that if we look at work done, notice that the units are the same. So in one sense, we are working out one and the same when we're talking about energy transferred, and also when we're talking about work done. Because if you look at the units of energy transferred here, you notice it's in joules, and also we're working out the units for work done in joules as well. And the equation stays the same. So the best way to understand power is to break it down here, as we have seen, and I'll repeat again. An energy transfer of 1 joule per second is equal to a power of 1 watt. Okay, now this holds true for this equation and this equation. Now we're going to move on to the change in thermal energy, and this can be represented as delta E. And what we're talking about is the amount of energy stored or released from a system. So if a system is storing energy, it's known as potential energy. And a system can either store energy or it can release the energy. And when we're talking about a change in thermal energy, we're simply talking about the amount of energy stored or released from a system as the temperature changes. And this is crucial, as the temperature changes. And this can be represented in an equation which has a component known as specific heat capacity. And this will vary for any substance that we are dealing with. So specific heat capacity, there is a practical that is linked to this, and it's a more of an in-depth topic. But I'm going to introduce you to this equation here, and then we'll go on to how thermal energy is being transferred in systems, and we will come back and look at this equation in more detail. But it's good to just be introduced to this equation now, and we'll go through the way thermal energy moves around a system. But bear in mind that this equation, we will look at it in a bit more detail, and we'll look at it in terms of a demonstration or a practical element where we can see this in practice. So let's look at this equation now. So here we have the word equation for change in thermal energy. And as you can see, it's mass times specific heat capacity multiplied by the temperature change. And we represent all of this by this equation here. This is the simplest way to represent that equation. And the triangle before the capital E simply means change in. So the change in energy represented as here. And we have, again, you're seeing the same units, joules when we're talking about energy. Mass is in kilograms, and specific heat capacity is joules per kilogram per degree Celsius. And this is how we identify it there. Temperature change, again, so you're noticing something similar here. When we're talking about the change in something or change in a value, in physics and maths, we can represent it with this triangle. and change in temperature in degrees Celsius. Now, you do not need to remember this equation off by heart. It will be given in the equation sheet or the equation formula that will be given with your test paper. However, you should understand how to apply this equation in any given situation that relates to specific heat capacity or the change in thermal energy of a system. So you may be asked with questions revolving around specific heat capacity, or you may be asked in terms of the change in thermal energy. In any case, you should be able to apply this equation, and you should be able to apply it correctly to get your answer. So the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degrees. This is why we get joules per kilogram per degree Celsius. So it's the temperature it's the energy that is required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So we say joules per kilogram per degree Celsius can be represented as shown here. So can you take down the breakdown of this equation for change in thermal energy? Make sure that you space out your notes clearly, showing the units involved and how we are representing the symbols as well for this equation. Once you've done that, I'm going to move on now to the PowerPoint. So I'm going to break from the notes here, and I'm going to show you a PowerPoint through Teams where we will discuss and look at how thermal energy can be represented in a system. So make sure you take this down, and let's put 4 minutes to make sure that you have this equation down clearly with the correct units represented. If you're not able to take this down in time, when I move on, within about 4 to 5 minutes, I will move on to the PowerPoint. If you have not taken down any of the notes here, it's gone, maybe you've taken a bit more time, you can always replay these videos back at home to make sure your notes are up to date.